Welcome you to session 6 here in the Diamond Hall. And good morning, everybody. I welcome you on behalf of my co-chair, Professor Tony Arangelovsky, and me, Peter Mark, coming from Bochum University as well as Skopje University. And welcome to this session. Let me introduce, first of all, our keynote speaker, Professor Albert de la Fuente. And Albert, we're very happy that you're here today, sharing your knowledge with us. Professor Albert de la Fuente is a full professor at the University of Politécnica de Catalunya, Barcelona, Spain. And he's founder of the C3S group, and the 3S are standing for sustainability, smartness, and structures. And his research focus on fiber-reinforced concrete, 3D printing with cement-based materials, sustainability assessment, and we all know he's author of several papers in journals, in conferences, supervises lots of PhD students. And to underline his understanding in sustainability, he is a coordinator of the European Union founded project Boost, is Circularity Boost, FIP Fellow, and he is the co-chair of the Commission 7 for Sustainability and also founder of a spin-off. So, Albert, thank you very much for coming once again. The floor is yours, and the presentation will be held on sustainability of smart 3D printed concrete structures. Sorry that, Albert.
No
please,
problem.
We are looking forward.
No problem. Thank you very much, Peter, for your kind introduction. Thank you both chairs. I think there is kind of echo. No? Okay, good. First of all, I want to thank you very much, Darko, and the organization for inviting me to this event. Yesterday, I noticed that you are a brotherhood, and that you know how to enjoy the time. Also do technical events, but I value a lot the way you enjoy and the way that you have organized this event. Thank you very much for the invitation. For me, it's something that I will remember for a long time. Thank you very much. Good. When Darko contacted me for this topic, say, Albert, make a speech related to 3D printing. If you can put also sustainability, also something related to the artificial intelligence. I was thinking, Darko, you are asking too much to me. I'm not a really expert on this topic. I know a bit of everything, but I said, okay, I like challenges. And I also like to be honest and transparent. And I will be honest and transparent with what I think I know about 3D printing in construction. Because we hear a lot of 3D printing, we hear a lot about sustainability, but someone has still not proven that this technology is sustainable nowadays. So I will try to do something in this line. If not, sorry. Well, I will start with from the beginning. From who were the inducers and the researchers that started with the 3D printing technology. And you can see from the picture and for the color of the picture that it's time ago. So, first message, we are not inventing anything. There were others that already researched on 3D printing. In this case was William Herschel, in the United States. He patented a system which consists in a vertical pillar. Let me see if I can do something here. Which acts as a pivot, and here we have an arm that can rotate vertically 90 degrees, and then here we have two adjustable curved plates from which we pull the concrete. And with this movement, vertical movement of the pivot, together with the vertical displacement of this level arm, and also the rotation, circumferential rotation, he was able to produce these type of structures, domes. This time. There were another. Sorry, I didn't want to be there was yeah, thank you. Yeah, there was Madoc that also made some new implementations on his patent, and then Walsworthy and Hardesty, yeah, made some modifications and enhancements that served to validate the patent. But at the end, we consider Urschel as the first researcher and the pioneer in the 3D printing concrete area. Yeah? Let me show this video. It's very short, but for you to, it's from YouTube. Yeah. See, of course, it's accelerated, but see, it's a backlit. Yeah, that it's automatized, receives the sand and the cement, and makes the mixture. Yeah, well, keeps in movement. Yeah? Also, the system provides the water for the mixing. Yeah. See at the end the capacity. Opa, sorry, I have to come back here and here. Yeah. Then there is another video. Yeah. See this from the structural perspective or the capacity of generating different geometries. See that in this case are mainly. Yeah. Are mainly circular. Yeah? So deposits, shelters, some housing. If someone wants to live in a circular house, which is not probably very appealing, yeah. Let me show you now the video. Yeah, this in color. It's from the same, from Urschel, the same. Yeah, it's large. Yeah, but let me only show. They enjoy, of course, the construction. Yeah, there is another thing here that I like a lot. It's very representative. Yeah, there is. See that there is only two operators. The one who's pouring the material into the bucket, and then the other one that it's controlling the geometry and the finishing of the concrete layers. Yeah. There is at this point something that I like. I probably already missed. Here, wet work. Yeah. This is funny. I mean, and at the end, of course, they had also to do arrangements for the system to work. Yeah, but I mean, at that time there was not quality control for this type of material. So you see that the same operators could add water. Yeah, then modify the water cement relation. Yeah? So it's very manual. But the thing is that it's self-construction. Yeah? We can consider also self-construction. And another interesting thing I want to point out is that since 10 years ago, we are making the most to integrate women in the construction. Yeah, in this case, she's bringing the watermelon, but not only that. She joins the breakfast or whatever, but see that she will end up working, because the manual work does not require big amount of force. Yeah, so she's collaborating, she's embedded in the system. So at that time, they were already thinking in introducing women or compatibilize the technology so that women could enter in this sector in a natural way. The finishing, and see that there's still some manual work, for finishing the dome. And at the end, I think there's a picture here. With the house finished. Another thing is if you want to live or someone want to live here, but at that time there was this possibility. Thank you much, I can do it. So another question could be, why, if this technology already exists, why this technology was not implemented in other jobs in which the geometry, the challenges to produce the formwork, the 3D printing was not introduced. See, I have here two examples. In Spain, probably you are familiar with. The first is Hippodrome. It's the stadium for horse races. Was designed and constructed by the engineer Eduardo Roja. Yeah, these are hyperboloic curves. Yeah, they require very complicated formwork. Yeah, and here probably you already know. Also, this in Valencia is the restaurant of the oceanographic. Yeah, so it was designed by Pedro Serna, or at least the material. But see that there is a huge need of formwork and complicated to be constructed. Yeah? Why not to use 3D printing in these constructions? Because at this time, the reason mainly it's because the cost of the formwork and the cost of the labor force was low. Yeah, and did not justify at that moment the use of other systems that implies the avoidance of formwork or the labor force. Yeah, this was the main reason. Yeah, also because in parallel it exists the shotcrete. Yeah, shotcrete is a very similar technology. At the end, is also the concrete can be shotcreted manually. Yeah, or even with a robot. It's robotized. So at the end, it's kind of 3D printing construction. The unique difference is that in these cases, the formwork is the soil. Yeah, but the concept is very similar. So we were not using the 3D printing technology first because the concrete in situ or the pre-stressed concrete technology has been advanced during 100 years and it's really optimized. Yeah, and also because the cost of the labor force and the cost of the formwork were not sufficiently high to justify or in other words, was, let's say, balanced with the productivity with the existing methods. Yeah? But we have a challenge. Well, we have several. Yeah? The increase of global temperature due to construction. See these graphs starts right after the Industrial Revolution. Yeah, and here is when the construction in high number started, and see that there is a direct correlation between the warming potential or the CO2 emissions with the increase of temperature. Of course, this increase of temperature is not only due to the construction, yeah, but we are one of the main promoters. So this is one of the reasons that bring us or lead us to think that we have to change something in the concrete construction. We are doing, of course, yeah, we are optimizing, yeah, using topology or reducing the CO2 in the cement or using more efficient mixtures, but we still to do more. Yeah. So I present, or 3D printed concrete is presented as a technology that provides freedom of geometries, increase of productivity, and other things. Yeah. But one of the things that promotes is the material reduction and the CO2 emissions, both in up to 30 and 40% respectively. Yeah. So these aspects are interesting. Yeah. If we want to reduce the impact in construction, we have to go through these new methodologies, or at least give them an opportunity. Yeah. Then we will see. So for that, yeah, in terms of sustainability, what I'm going to present is the comparison from sustainability perspective of a footbridge, yeah, of 12 meters of a span. It's a real footbridge that has been constructed for pedestrians. Yeah? It's one made of concrete, traditional concrete, another made with 3D printing, another made with reinforced concrete, but reducing the weight of the web. Sorry, and then another option made of ultra high performance concrete, and another option made of textile reinforced concrete. Okay, so we are going to compare these solutions. These solutions are designed for the same purpose, with the same boundary conditions, for the same capacity. So, from a technical perspective, all of them are comparable. Yeah. First of all, let me introduce in 10 minutes, yeah, the construction of the 3D printing footbridge. Yeah, there are several 3D printing methodologies. Yeah, the one we are going to use is this. Yeah, is the method that was proposed by Enrico Dini in 2004, and it's very similar to the 3D printing method that is used for producing plastics. What we do is to pour material, and then we have injectors that pour water in those areas in which we want the concrete to hydrate and to generate the section. Yeah? Have here a picture, a video for you to see. Yeah? It's a huge machine. Yeah, it's 4 meters long, 2 meters wide, and then 8 meters in height. Yeah, see that first we have a layer of material, and then we pour water in those. Here we wanted to produce concrete cubes to be tested. Yeah, we wanted to characterize the material. Yeah, so see, you have a second pass of water, and then we have extension of more material. But here, during the extension, we are also compacting. There is a roller, we cannot see it, that weighs 80 kilos, that compacts the material. Yeah? So this is the main idea of the system. We can discuss if this is efficient, productive, or not. Yeah, this is not the point of discussion. Yeah, it's a method that we use for producing this bridge. Yeah. Let me explain you a bit of the story of the material, if technology allows me. Yeah. First, we had in the laboratory a small printer, yeah, to produce some mixes, because we wanted to know which is the effect of the thickness of the layer, yeah, each of the layers, and we wanted to also to check which is the effect of the orientation of the layers with the direction of the force towards that we are testing. Yeah, for that we produced slabs. Then when we cut in different directions, yeah, and then we tested flexural, compression, and modulus of elasticity. I'm going fast in this because I want to only show you the capacity of the material. First, we noticed that for the water to percolate from one layer to another, maximum thickness was 5 centimeters. We started with 7 and 8, but we noticed that there were layers that were not hydrated. Yeah, so we reduced the thickness to 5 millimeters, and this lead us to guarantee the full hydration of the layer. Yeah? In terms of strength, see that there is a direct correlation between the density and the strength. The higher the density, the higher the strength. But the important is that with this system in the mini printer, we reached consistently compressive strength up to 20 megapascals. Yeah? It's something. Yeah, we have to improve it. Another thing that we notice is that that in terms of compressive strength for the different mixes that we tested, there is huge difference between the energy of compaction with the roller. Yeah, for low compaction, maximum 20 megapascals. For high compaction, in some cases up to 60 megapascals. Yeah, so compaction is an important thing. Another important thing is that in terms of hydration and testing at 28 days, there is no statistical difference between curing the pieces in a water tank submerged or curing in the room. This is interesting because this system of dropping water is not efficient from the curing perspective. Yeah, but it seems that it's not necessary to induce more humidity for reaching the same degree of hydration. It means that we don't need any curing chamber to cure the specimens, and these specimens could be cured in the normal conditions because we will reach very similar strength. Yeah? Then this is the flexural tensile strength. There are fibers in these materials. Yeah, we have to use fibers. And the important thing is that we are testing the elements in different directions, respect to the position of the layers, and see that there are two directions that have very similar behavior. These are average curves results for different materials. But the important thing is that there is a direction which is weak. Yeah. So if we have efforts in this direction, we have a problem. Yeah? So for that, what we have to do is to guarantee that the direction of the layers are compatible in terms of mechanical capacity. Yeah? So we see also that there is a direct relation between density and flexural strength. And if we reach density superior to 2000 kilos per cubic meter, we have consistently compressive strength above 40 megapascals. Yeah? Then we produced specimens in the real scale machine, 3D printer, and we did the same thing. We cut cylinders, and we tested the cylinders in different directions, in compression and the modulus of elasticity. Yeah? The same. The higher is the density, the higher is the compressive strength. Very similar. Yeah. An important thing is that if the density is superior to 2.2 kilos per cubic meter, we can reach characteristic values, and value which is exceeded the 95% of the occasions, superior to 30 megapascals. This, from the structural perspective, it's very interesting. Another thing is that if we test in different directions, we don't notice any difference in terms of compression. So the layers, yeah, could be in different positions respect of the load, that at the end we will obtain the similar, a very similar behavior in terms of compression. This makes the material homogeneous, something that didn't happen in the small machine. Yeah, so there is kind of a size effect here. So in conclusions and for designing, yeah, we end up with the conclusion that this is an isotropic material in the 3D printing, and we proposed these average values for the design with this coefficient of variation and a partial safety factors between 1.5 for compression and up to 3 for the residual strength. This is very important, right? Because if we are going to construct a footbridge with this system, yeah, we have also to evaluate which is the reliability that we have with this material, because at the end someone has to sign and someone has to sleep also, yeah, in calm, the person that has signed it. Yeah, so we also did. So this is the footbridge that we constructed. I'm not entering in the aesthetics. Yeah, I do like it, but it's the bridge that we constructed. For me, it's more of Flintstones bridge, something from the past. Yeah, but at the end, here what we wanted is to reach a geometry, see that is very natural, very organic, that cannot be produced, constructed with normal frameworks, and if so, spending a lot of money. Yeah. This footbridge consists of 8 segments that were produced in this machine, in this 3D printer. Yeah. One thing important is the amount of shrinkage that can be produced. Yeah. So almost 4,000 micro deformations. This is a lot. Yeah. So for that we need good curing and skin reinforcement that was made with steel fibers. Yeah. We then stored the elements outside. We produced it. I mean, we put it, all of them, in a metallic arch. Yeah. Then we blocked the joints, and then we sprayed concrete. Yeah. And one important thing that I want to disclose here: this bridge was in Spain proclaimed to be the first footbridge with only concrete 3D printed. But in reality, I said I want to be honest and transparent. Here inside, there is the arch. It was not necessary. It was necessary only for construction. In reality, after the calculations and the assessment, was not necessary this arch in the real site. But, and I perfectly understand the company, was in this case Acciona, that they invested a lot in this machine and this technology. If we would have failed in this first pilot, I mean, if this has broken during the placement or the first days, we have ruined the technology. Yeah. So from the social perspective and also from the marketing of the company, this would have been catastrophic. Yeah. For the technology, which is valid and feasible, and also for the company. So that's why we decided to keep the steel inside as an additional safety measure, because, as I said, was not necessary. Yeah. This was some views of the footbridge. We had to also spread resin on the top of the slab because to avoid it was very slippery. Yeah, to avoid accidents. And then we placed the beam. Yeah, this bridge in one day. The foundations were already prepared, so the construction period lasted 1 day inside. Yeah, of course, in the plant. We were producing during 2 weeks the elements. Yeah? And here, yeah, the inauguration date, all of them politics. None of the engineers that were thinking and risking for this are here, but something that it's, I think, extendable in all of the countries. Yeah? The first proof of load, yeah, loading test, was successful. And something else to be added here. See that there some glass protection here, and it's for two things. Yeah, it's to avoid children or kids to put their head inside. Yeah, this probably was not accidental. It was probably I mean, well, I'm not entering in the detail of the nature of the action. And the other thing is that for vandalism, I mean, this is a very isostatic structure. If someone comes during the night and destroys the web here, yeah, this is very sensitive because we have the maximum shear here. Yeah, that's why we put there. So to summarize this part, so it's feasible. We can construct the structural elements. Yeah, and the important thing is that the mechanical properties of this material are different from mortars or from concrete. I use several times the word concrete here, but in reality, this is a mortar. Yeah? There's still a lot to be done. Yeah, we are now working in other geometries based on nature, based also on the human skeleton or mammals. Yeah, because these shapes are optimized to only work in compression, minimizing the amount of calcium. Yeah, so we have to learn a lot from this, and we are start producing the first drawings and the first ideas based on these shapes. Yeah. We have also some projects in Spain, yeah, for using typology optimization to reduce the amount of materials in prestressed concrete girders to be used in bridges, and also we are producing a new footbridge, in this case 20 meters long. This is a render, yeah, it's still not constructed, but it will be constructed within the next 6 months, sorry, and it will be a piece, yeah, several pieces that we post-tension it and and placed in this river. Yeah. Now we are working with other methodologies for optimizing the production. What we do is to embed wireless sensors that measure temperature and humidity, and we embed these sensors in the layers, and with the temperature and with maturity curves, we can know which is the real strength in time without testing, and then we can, in this way, optimize the velocity of the printer. Yeah, because if the concrete is hardening at high velocity, it means that we can increase the load, and if we can increase the load, it means that we can go faster and produce faster. Yeah, and then with artificial intelligence and with data that we are generating during the production, we can reduce the cement amount of the mix, and we can do a lot of things. We are working on this area, which is very interesting and very promising, and at the end will close the cycle in terms of the 3D printing plus technologies to optimize production. Good. It's 1 minute. I have 5 minutes. Do you think I can extend 4 minutes, or otherwise I can make a large
Make
sum?
a compromise, let's say 3.
3? Okay, perfect. 2 minutes. Okay. So as I said, we wanted to compare different alternatives. Yeah. First, 3D printing. Another is the reference, the concrete, a reinforced concrete. Another reinforced concrete, but with a truss geometry. I mean, reducing the weight in the webs. Ultra high performance fire force concrete, and then the carbon fiber textile force concrete. So we wanted to consider economic, environmental, and social aspects for making the decisions, because we always say this is more sustainable because we are reducing the amount of CO2 that we emit. Is this sufficient to say that something is more sustainable than another existing alternative? Probably yes, but not necessarily. But because if for this reduction we are expending the double for reducing 10% of CO2 emission, this increase of cost is not efficient. That does not justify it, because probably this increase of cost, talking for instance on a public system, could be invested in researching cancer, for instance. Yeah. So now we enter in a phase in which not only CO2 emissions or energy, but also balancing cost and the social impact. And for this, we use a methodology which is my best. I'm not entering in any detail, but what we do is to identify the economic, environmental, and social criteria, and then the indicators that are representative to these criteria. These tree of requirements is settled with engineers, with the public investors, with funds, yeah? And then we establish weights for each of the criterias. Yeah. And the next question will be, okay, what do you obtain? What we obtain is a sustainability index for each of the alternative. And how? If we are summing euros with CO2 and with joules per kilo, yeah, or accidents. Yeah? What we do is to use the value functions. Value functions are used to prioritize and also to adimensionalize. I mean, for instance, for the economic criteria, let me give you an example. We are agreed that if we increase the cost, the satisfaction that goes beyond 0 to 1 has to decrease, right? And if we reduce the cost, the satisfaction has to increase. But we have to decide this shape, yeah? The first thing that we do is to the horizontal axis, which is the cost, we make it relative to the cost of the reference, yeah? So that's why we have between 1, which will be the reference solution, up to 3, yeah? See that for the reference solution, concrete solution, we have already 85% of the satisfaction because this solution is very, very optimized. Yeah, because we were doing this for more than 60 years, so it's optimized. And if we want to have the maximum satisfaction in terms of cost, we have to reduce still 50% of the cost. Yeah, and see that the alternatives that we are studying, in some cases, this is ultra high performance concrete. This is the concrete with the reduction of weight in the webs, and this is the 3D printing technology. It's very, very expensive. Yeah, there are reasons for that. I'm not explaining here. So we use these functions. Yeah, and with these functions, at the end, what we do is see that we have non-dimensional index and weights. So we multiply and sum, and what we have is the sustainability index of each of the alternatives. See that for the reference is 64%, for the 3D printing suspended, less than 50. The reinforced concrete with optimized weight in the webs, 75, and the most sustainable, the ultra high performance concrete. Yeah, and the very last, the one with the textile reinforcement. Yeah, we can simulate different scenarios with different weights, but always the ultra high performance and the reinforced concrete with the weight reduction is the one that has the major sustainability index. The 3D printing only increases when we increase the weight in the environmental and social aspects. From economic, loss. Yeah. So for concluding, yeah, because I extended 2 minutes, or almost 3. First, these conclusions should be framed to these examples. Yeah, we cannot extend to any type of building or footbridge or any other structure. These results are for these. The important thing, yeah, is that we were able with the 3D printing solution to reduce 40% of the material and 25% of the CO2 emissions, as we promised at the beginning. Yeah, the thing is that the costs are not permissible, yeah, for this solution. But this doesn't mean that we have not to continue, yeah, because we have to still research and we will optimize. Yeah, because also one thing is that when we calculated the cost of the 3D printed footbridge, we considered an amortization period of this machine of 2 years, when normally it should be 10 or 15. We were very aggressive. Yeah? And the reference solution is always the most sustainable when the cost is the decision driver. Yeah? Which makes sense. Yeah? Well, there are plenty of footbridges already in service. These are the references in case that you want to deep into. And for finalizing, I have and I want and I should give thanks a lot to my team, because they are the ones that do these things. Not only this, but they are the heart of the group. Yeah, so I'm here only expressing and transmitting what we do there, but they are the heart of the group. Yeah. Thank you very much for your attention.
Thank you very much, Professor De La Fuente, for your inspiring talk on showing what is possible nowadays with concrete. And I personally very much like that you showed all 3 columns of sustainability, not only the environmental aspect, but also economy and social aspects.
Exactly.
Okay, we should allow ourselves one or two short questions. What are your questions to Professor De La Fuente?
Attack.
If not, Oh, there's a question. Please.
Puedes en español, sin problema. But probably the others, I think it's fair. You can make the question in Spanish. We want to practice. Then I'll answer in Macedonian today, only today.
La obra de arte de Gaudí es muy conocida en su país y quería preguntar
Put it on, please.
Yeah.
The micro is not working.
Yeah.
Sí, porque la obra de arte de Gaudí es muy conocida.
Sí.
Quería preguntar si, porque su accente se pone en la naturaleza también, si usted también utiliza eso en su país
Sí.
o es una inspiración de él.
Oh, yes. Thank you very much for your question. She's asking that, and she's very right in this case. The Gaudí, he was using in his designs, he was inspired in nature. Yeah? So very complicated shapes that the architects and engineers were suffering there in Barcelona for the construction. It's complicated. But what we do, it's a mix. Yeah? We produce the molds with 3D printing, and then we fill. It's another way, yeah? So 3D printing is being used in the construction of the Sagrada Familia, but not for producing the structure, but for producing the molds that will be filled and then placed in the structure. So, yeah, I hope that this answers your question. Thank you very much.
Okay, thank you very much once again for the concrete and the language lesson. And thank you. Now I invite the president to give the appreciation document. Thank you. And I hand over the chair to my colleague, Professor Arangelovski.
Thank you, Professor Mark. Сега следи вториот дел, во кој што е блокот на презентации на спонзорите. Во оваа група, значи, се сребрените спонзори, 100 куќа, 100 сех, Штрабак, Титан Усие и WB&E. Па ќе ги замолам представниците на компаниите, започнувајќи од првата, 100 куќа. Значи ќе биде прикажано видео презентација на компанијата. Ова беше за заедничка презентација на двете компании 100 куќа и 100 сех. Сега продолжуваме со наредниот сребрен спонзор, Штрабак. Повторно ќе биде кратко видео презентација.
Every day the sun rises.
Life never stops.
Just like at Strabag. Day upon day, we shift tons of materials around the world. From global to local. From micro to mega. we move from analog to digital. By people, for people. And on it goes, from high up in the air to deep down in the ground. From large-scale industrial projects to social housing, from development to operation, from the path to the destination.
This is why we are always on the lookout for new paths.
We use innovative technologies to build better and safer, and are constantly developing our processes and materials. From conception and construction, and from facility management to conversion, we keep on moving, because movement means change. And if as one of the biggest construction companies we make a change, then a lot of other things change too. We don't just talk about progress, we work on it. Strabag. Work on progress.
Дали се уште има? Дали има представник од компанијата Strabag кој ќе ја продолжи презентацијата на компанијата? Наредно представување на сребрениот спонзор цементарница Усие, групација Титан. Повикувам представникот на компанијата.
Почитувани, денес имам чест да представам една компанија која веќе 70 години произведува најквалитетни градежни материјали со најголема издржливост и најголема сигурност и представува столб на нашата индустрија. Тоа е компанијата Титанусија. Низ своето постоење, Титанусија учествувала во градењето на повеќето, речиси сите капитални објекти што биле во државата пошироко. Титанусија е дел од групација, од Титан групацијата, која постои од 1902 година. Делиме заедничка цел, тоа е да го направиме светот околу нас побезбедно, пооддржливо и поудобно место за живење. Од големо значење ни се релациите што ги градиме со нашите деловни партнери, со нашите соработници, со локалната седница, со академијата. Посебно ни е значено релацијата со академијата, преку организација на вакви семинари, симпозиуми, конференции, ни значат многу и ни носат голем допринос во заедничкиот пат што треба да го изодиме кон зелена транзиција. Како што знаеме, 2050 година индустријата треба да е карбон неутрална или градежните производи во нашата индустрија треба да се со нула емисии на јаглерод. Ние сме исто обврзани тоа да го постигнеме на најразлични методи со користење на алтернативни горива, оптимизирање на процесите, замена на клинкерот со соодветни материјали, користење на SCM или Supplementary Cementitious Materials по нашите производи, нови проекти како проектите за фаќање на некој начин на јаглеродот емитуван и депонирање на таквиот јаглерод. Нашето портфолио на производи се состои од зелени производи, што означува дека се со намалена јаглеродна емисија, но со задржани перформанси, дури и со појачани перформанси во однос на конвенционалните. Како позитивен пример од нашата групација би искористил да спомнам компанијата Интербетон, која што на локално ниво во Грција произведува 2,5 милиони кубни метри бетон и најпродаван продукт е бетон со комерцијално име Велтер, каде што се користи, каде што за да се произведе има 30% помалце емисии, односно кога би дошло до LEED сертификација, ќе ослободи до 90 кг на метар квадратен јаглерод диоксид. Уште еднашка сакам да се заблагодарам на фейлата и на индустријата за доприносот, за ова да го оствариме заедничко, оваа зелена транзиција и ви благодарам на вниманието.
И последниот во оваа група е спонзорот WB&E. Молам представникот на компанијата да ја представи својата компанија.
Почитувани присутни, јас сум Јована, градежни инженер од компанијата Williams Building and Engineering. Компанијата постои повеќе од 5 години на нашиот пазар, има канцелари моментално во Македонија, Белгија и во Португалија. Тимовите во овие сите 3 канцелари бројат преку 20 на луѓе и најчесто нашите проекти се заедничка соработка помеѓу сите 3 канцелари. Главна дејност на нас е фасадно инженерство, како и 3D моделирање на фасадни конструкции и врските помеѓу нив. За статичката пресметка на фасадните елементи користиме еврокодови и национални анекси, додека 3D моделите во софтверот HiCAD кој го користиме за моделирање ги следат техничките и индустријските стандарди. Од досегашните сработени проекти, фасадните конструкции може да ги поделиме на вентилирани, стаклени и комбинирани системи. 3D моделите кои што ги изработуваме го користиме софтверот HiCAD и на следните слайдови ќе покажам некои од објектите кои што ние ги имаме изработено. На овој слайд може да видиме објект кој се наоѓа во Антверп, Белгија. Се прикажани слики од изгледа, како и 3D модел од софтверот, Кај што може да видиме, ова представа типичен пример на вентилирана фасада, односно имаме касета, под конструкција составена од упрофили, како и анкери кои представуваат врска помеѓу фасадната конструкција и објектот. На следниот слайд може да видиме објект кој се наоѓа исто така во Белгија, Остенде. Имаме слика од архитектура, слика од објектот во изградба и модел кој што ние го имаме изработено во 3D софтверот HiCAD. Ова представа посебен вид на конструкција, каде што фасадните панели се од материјал неолит и за таа цел го имаме моделирано како 3D солид елементи. На овој слайд може да видиме објект трговски центар кој што се наоѓа во Порто, Португалија. На овој објект го имаме работена кровната конструкција која што може да кажеме дека представува стаклена фасада. Како последен пример кој што сакам да го покажам е доста интересен објект, односно се 4 железнички станици на кои што ние имаме изработена фасадната конструкција. На овој слайд може да видиме слики од веќе изведен објект, како и слики од 3D моделот кој што ние го имаме изработено. На овој објект имаме користено малку поинаков пристап на моделирање, односно параметарско моделирање. Што представува параметарско моделирање? Самиот софтвер овозможува еден елемент кој го градиме, односно креираме, сите варијанти на еден елемент да ги ставиме во еден. Односно, секој додавање на фланша, отвор, горе, долу, лево, десно, да биде зависен од варијабли. Тие варијабли може да ги ставиме во мени и тој елемент го да го зачуваме во каталог. И подоцна, кога го креираме фасадата, може да креираме поле, може да креираме шема од полиња, да го повикаме елементот кој што го имаме зачувано во каталогот и за секој поле да избереме различни варијанти на елементот кој што веќе го имаме креирано. Како резиме, можам да кажам дека 3D моделите кои што ги креираме во HiCAD возможуваат директно да извадиме работилнички цртежи, како и предмер и можност за параметарско моделирање, со што начинот на нашата работа се доста оптимизира. И за крај ќе оставам QR код кој што доколку го скенирате ќе однесе до нашиот LinkedIn профил, каде што најчесто споделуваме тековни објекти кои што ги работиме. И бидејќи презентацијата е ограничена на време, доколку некој има одредени прашања, ќе поканам да го посетите нашиот штанд. Ви благодарам на вниманието.
Да изразам уште еднаш голема благодарност до сите наши спонзори кои што помогнаа во организирањето на 21-иот симпозиум на Друштвото на градежни конструктори на Македонија. Сега ќе продолжиме со вториот дел од сесијата и повторно предам председавањето на професор Петер Марк.
Okay, ladies and gentlemen, now we come to parallel session. It's the session number 6-1 here in the Diamond Hall. And I announce the first speaker being Boydar Yanev, and he will talk on robustness, resilience as sustainability as engineering and economic criteria of bridge management. Mr. Yanev, the floor is yours.
Distinguished chairs, dear colleagues, thank you for this opportunity to present my train of thought. I have a problem. Maybe you help me arrive at a solution. As you know, management is about taking decisions and executing them under constraints. Now, what constraints are there? Intelligence, information, energy, time, space, money. I challenge you to find others that aren't. Different places, different priorities. Europe is concerned with energy. The United States is concerned with time. Japan with space. China, I don't know if they're concerned with anything. They seem to have it all. Now, information is no longer a constraint. We have more information than we need. Intelligence, ever since Descartes, everybody is very intelligent. Now, what is the situation in the United States where my experience is? There are 650,000 vehicular bridges, 220,000 railroad bridges, they're old. More than 40% are more than 50 years old. This is the concentration of the bridges. So it looks a little bit like a head and a body, but the analogy is very loose. Now, in New York, where I come from, there are lots of record-breaking bridges, but the last record was established in 1964. It's amazing how everything I show here is the work of Ottmar Ammann, Swiss, educated by Kuhlmann. My experience as a city employee for 30 years was more with the city bridges, and they're even older. And it was all started with the genius Roebling, a German and student of Hegel. But these are the so-called East River bridges: Brooklyn, Williamsburg, Manhattan, and Queensboro. Now, my viewpoint has been privileged. I have been able to look from down up and from the top down, and it's very important to keep balance. To keep balance, you need a balancing rod. We were taught to balance between energy and intelligence, but then we were taught to balance between economic networks and performant projects. And we started lurching, which is not good if you're on a cable, from the affordable to the safe, back. These cycles became habitual. Then we got more intelligent, and we started doing simultaneously the performance and the economics. But economics we are reducing, whereas the performance we are increasing. Now, this is contradictory. What is the big contradiction? In engineering, we supply by a factor, and that's a legal factor, more than the demand. In economics, they make sure the demand is more than the supply. Now, there are no economists here, right? Right? No. When they meet the economists, there are no engineers there. So that's why we don't understand each other. Now, in the meantime, in society, certain things tend to happen. Now, we had COVID, and you see the curve, the red one is in the United States. We have the future tech hype cycle, and you see a similar curve. We have the Higgs ratchet effect. Now, Higgs is an economist, and his effect is something else. He is against government, and as a result, he observes that when there is a crisis like those, that's a crisis. So when there is a crisis, the government expands in order to take care of it. And when the crisis is over, it does not shrink, and that bothers him. Now, this one is where I come in. This is a set of reports about potential hazards on the 800 New York City bridges from 82 to 2006, and they jumped from 100 or so to 3,200, and then back again, but to 1,200. Now, this is not because we tried to cheat and have more employees. This is because things never get back to where they used to be. Now, look, we said never again, but later on, the same thing happened again. These reports for potential hazards now for New York State are from 2000 to 2022. So there is something symptomatic about these crises. I decided that there is an analogy to the von Mises stress. Why? The von Mises stress can fail in three different ways. Each member can have no strength. Each member can buckle. The whole system can buckle even if the members do not buckle. It can flip down. So these three ways of failing, if you look, you can say our demand increased precipitously. You can also say the supply we gave of service, that decreased, they're like reciprocal. Now, in the meantime, people start talking about sustainability. Now, Henri Léon Lebesgue, a long time ago, said if you introduce a new term, this new term has to be defined by at least one new category. So what do I say? If there is sustainability, and that's the new term, let's define it by robustness and resilience. Now, what's robustness? It's a descriptive term, ability of the structure impaired to meet the demand. What's resilient? The same thing, but over time. So let's say robustness is in space and resilience in time. Now, we are not going to invent new stuff. There is time, there is money, and there is energy. Unfortunately, we already know politicians go in time, economists in money, and we engineers in energy. So all I say is let's rotate the axis, and let's say there is sustainability which will engage simultaneously engineers and economists. There is resilience and there is robustness. And with this rotation, we may get to talk to each other finally and to work together. So you've seen this picture, and this picture is in the engineering domain of time and energy. We have designed the structure, it declines, there is an extreme event, then if we can, we fix it. Let's use the new plane and say there is the demand, there is the service life, the demand increases, then there is an extreme event, it jumps up, and eventually maybe we manage it. And if there are two variables defining the third, robustness and resilience, defining the sustainability, we maybe can do a Fourier analysis and find which combination can lead to a crisis. And so that we avoid a situation where the supply keeps declining and the demand keeps increasing, because we know these happen. Examples. I'll try to be quick. Marianas Bridge, a structure that had no robustness and it had no resilience, collapse. Now, this is interesting. These are two pictures from the Bay Area in '89. Oakland, the structure had no robustness and it had no resilience, and it collapsed and killed 41 people. On the other side, in Trocadero, the structure did not have robustness, but it did have resilience, and it killed nobody. It was still a structure that was not sustainable, had to be removed, but it was resilient. And there are many more examples. Now, the Baltimore Bridge last year, 366-meter span, was good in 1977. It was not good in 2024. Now, they're planning a bridge with 488-meter span. It's good now. Is it going to be good in 50 years? Why are they not planning 700-meter span? It's doable. GW Bridge, in 31, one level. In 61, two levels. But it was planned. That's the way to go. Also Amman, the Bayonne Bay Bridge. Well, the deck level was hit many times. They raised it. 20 meters. It still works. Now, that here, a wink to Professor Brew Wheeler. Concrete, he says, is no good. Absolutely not good. And we design it for bending, and it fails in shear, and in corrosion. We need something else, definitely. Joints. The only good joint is no joint. And incidentally, they are not designed. There is no stress analysis for any of these. They take them off the shelf. For 30 years, I propose, let the university professors do a stress analysis. For 30 years, everybody votes in January, let's do it. But in April, when they meet and we're not there, they say, no. It has not happened. Now, there are also the signature bridges. Are they sustainable? Well, if you like them, maybe. This bridge costs about $6 billion. They could have done it for $2 billion, but it was not going to be signature. Now, that bridge, Why is it up there and so extraordinary? Because it was sustainable. Environmentally, it was the best solution. So first you build your bridge, and then you check if it's a signature bridge, not the other way around. Now, my friends, the Chinese, they build these bridges, and I ask them, do you know how this will look in 50 years? You've changed the geography. There's no way back now. You're committed. They say in 50 years we may be flying. They made this funny gesture. Maybe not. Our bridges from 120 years ago, we need them desperately. We can't do without them. So, where am I? Now I have to balance between robust, resilient product and sustainable process. And my cycles should need to get simultaneous and more refined, faster. Basically, it will be an improvement if we can do it. But when I sit on my cables or visit my favorite cities, I don't see this picture. All I see is this. So all I'm left with is holding with my two hands and trying to think. And so do you. Thank you.
Professor Janev, thank you very much for an inspiring talk and giving this view on bridge maintenance. Please, I ask to the audience, keep your questions for the coffee break or for the lunch break. Then we have all the discussions. And I announce Professor Angelovsky to announce the next speaker.
The second presentation in this session will be given by a group of authors, Nenad Pecic, Sasha Stosic, and Snezana Mašović, on paper with title Eurocode 2, Cracking in Prestressed Concrete. The presenter is Professor Pecic from the University of Belgrade, Faculty of Civil Engineering. The floor is yours.
Thank you. Dear colleagues, chairman, dear friends, our paper discusses Eurocode 2 regulations regarding cracking in prestressed concrete. Eurocode 2 allows the design of prestressed concrete elements with cracks for both unbonded and bonded tendons. And the following discusses the effectiveness of cracked prestressed element with bonded tendons. Serviceability limit state requirements regarding cracking are similar for both bonded and unbonded tendons. Allowable crack widths are given in the table. For unbonded tendons, they are rather wide, 0.3 or 0.4 millimeters. And this is the same as for the reinforced concrete elements. For bonded tendons, it's 0.2 millimeters. Ultimate limit state design limits the stress in the reinforcement to the level which provides that crack width is practically close or always below the 0.3 millimeters, particularly for the quasi-permanent load level. This means that the crack width requirement for unbonded tendons is always met, and the check is a matter of formality. For bonded tendons, the crack width limitation is more stricter. It's 0.2 millimeter, and the load level is higher, frequent combination. However, even that requirement is mostly fulfilled. In case that significant part of the cross-section is under compression, and this is due to pre-stressing, compressive force, the tensile strain on the cracked side of the section is smaller compared to the reinforced concrete. And the crack width is governed by the tensile strain primarily. So the corresponding crack width is often satisfactory. So where is the problem? For element with bonded tendons, there is additional requirement, so-called decompression limit. And it is set for almost all exposure classes except for XO or XC1, which we can classify as indoor use. The decompression limit requires that all parts of bonded tendons under the specified service load, which may be quasi-permanent or frequent, lie at least 25 millimeters within concreting compression. 25 millimeters is nationally determined parameter. And for example, in Germany, it is set to 100 millimeters. As a result, the tendons cannot be close to the potentially tensioned edge of the cross-section. This reduces the eccentricity of the provided tendons and consequently the produced compression reserve from pre-stressing. However, in most cases, if the tendons thus provided to comply with the compression limit are rearranged with maximum eccentricity that is available in the cross-section, in that adopted cross-section, the effect of pre-stressing is enhanced so that the same element can be shifted into a state without cracks or even to a fully compressed state. Several numerical experiments were conducted to evaluate the effects of that mentioned tendon rearrangement. All beams were equipped with tendons complying with the requirements of Eurocode 2 regarding duct spacing and covers. The number of tendons varied. Simple beams were considered in pairs, and the first beam from the pair used the maximum available eccentricity, while its companion beam had the tendons shifted towards the centroid of the cross-section. The paper presents two analyzed pairs of beams, named A and B and C and D. They all had an identical cross-section, but a different number of tendons per pair and a variable eccentricity. Beams A and B have 4 tendons and C and D 6 tendons. You can see also the compression limit on the figures, which is set 25 millimeters below the duct of the first row, since it is according to the decompression limit requirement. The decompression limit is determined according to the position of tendons, of course. Another required data, the jacking force was adopted according to the selected tendons. Initial and time-dependent losses were assumed. To ensure the validity of the specimens regarding other design requirements, stress check was performed for the pre-stressing stage and the final stage. Beams with maximum eccentricity, B and D, you can see that on the picture, were analyzed as uncracked, which included tension at the bottom of the section did not exceed mean value of tensile strength of concrete under the characteristic load combination, which is the maximum service load, and the neutral axis under the specified check load, which may be frequent or quasi-permanent, depending on exposure class, coincide with the decompression limit. And beams with raised tendons, A and C, were analyzed as cracked, so that neutral axis under the specified check load coincide with decompression limit. Observe that each pair of beams, A and B and C and D, is made of the same amount of structural materials. The load-bearing capacity regarding both ULS and SLS was compared for each pair of beams. Results for the second pair, C and D, are shown in the table. And we have values of resistances, its moments in the midspan for beams C and D, and as a result, in the example considered, the total load-bearing capacity of a cracked beam is about 15 to 16% lower compared to an element without cracks. The results for beams A and B are also presented in the paper and are similar. It is important to say that it can be shown with a series of calculations involving a gradual change in eccentricity that SLS bearing capacity determined from the decompression limit continuously decreases with the increase in the distance of the tendons from the tensioned edge of the cross-section. The maximum resistance regarding serviceability limit state requirement is obtained with maximum tendon eccentricity and provided that element has no cracks under service load. Conclusion: there is no benefit in designing pre-stressed cracked elements with bonded tendons according to Eurocode 2 when decompression limit is required. Or, in other words, design pre-stressed elements with cracks is a pure waste of structural materials. The optimal solution, as before, is obtained by designing elements without cracks based on limiting the stresses in the serviceability limit state. That was all. Thank you for your attention.
Thank you, Professor Pecic, for emphasizing the problem with cracking in pre-stressed concrete, especially when we allow a tensile stresses in the bottom edge of the section. So I think if there is any question, or we can leave it for the lunch break. Again, I'm hand over the chair to the Professor Peter Mark.
Okay, gentlemen, ladies, we'll come to the third presentation. It is given by Professor Sergei Kurilov and co-authored by Ayman Al-Fouli. And the title of the presentation is From Cracks to Collapse, Case Studies in Applied Element Method for Extreme Structural Analysis. Sergei, the floor is yours.
Thank you, Professor Mark, for the kind introduction, and for the language balance, I will now continue in Macedonian. Почитувани колеги, имам задоволство да представам еден заеднички труд со колегата Айман, кој што доаѓа од компанијата Applied Science International од Соединетите Американски држави. А мотивацијата за ова денешно излагање е во линија со мотото на овој симпозиум. Ќе зборувам за методи односно еден од методите за анализа на конструкции кој што се чини дека полека тангентно се приближува кон мотото на овој симпозиум, односно надминува голем број од ограничувањата кои што постојат. Изложувањето е организирано во неколку делови. На почеток прво мотивацијата, на многу накратко без навлегување во теоретските поставки околу методот на применети елементи, кој што е буквално преведен директно од англиски. На крајот ќе прикажам неколку примери од примената на овој метод кои што доаѓаат од нашата заедничка работа. Што е проблемот? Секако имаме различни типови на проблеми кои што ги решаваме во нашата област, дали се тоа материјални карактеристики кои што се непредвидливи или се многу хетерогени, или пак имаме можеби оптоварувања кои што се комплицирани. Затоа ни стојат на располагање повеќе различни методи, одека не е целта да ги набројам сите, само неколку од нив кои што наоѓаат примена во градежното конструкторство. Можеби не крунисан крал помеѓу нив е секако методот на конечни елементи. Меѓутоа и примена наоѓаат и методот на дискретни елементи, а во последно време, иако е релативно нов овој метод, 20 на години веќе постои методот на применети елементи. Што е проблемот со методот на конечни елементи? Има, да кажеме, потешкоти во однос на следење на комплетниот одговор на конструкцијата од линеарно однесување до лом. Особено има проблем во преносот, односно во трансферот на од една во друга состојба на некакво континуирано однесување во состојба во која што ќе ги следи пукнатините и понатаму ќе го проследи одговорот до лом, е ограничено во повеќе елементи за континуирано или симултано моделирање, големи деформации, пукнатини, одвојување на елементите или пак однесување кое што е во фазата на омекнување на материјалот, како и контактот помеѓу самите елементи, што представува одреден проблем во различни сценарија. На овој график се споредени овие три методи, многу накусо. Методот на конечни елементи има одлична примена и може и се применува во овие области на континуална, односно дискретна средина, меѓутоа за голем дел од проблемите не може да се автоматизира. Методот на дискретни елементи, па од друга страна, некако обратно, неговите позитивни карактеристики се истакнуваат кога се работи за средина во која што имаме некакви дисконтинуитети, одвојување на елементи и така натаму, меѓутоа во поедноставните случаи, условно кажано, има проблематична малку примена, а се чини дека методот на применети елементи ги надминува овие или балансирано помеѓу сите овие состојби на однесување на една конструкција. Накратко многу што е во суштина или како функционира овој метод, релативно едноставен, базиран е на методот на конечни елементи во логиката, нели? Ги моделира, ги представува материјалите, односно елементите како крути тела, крути форми кои што помеѓу себе се поврзани со федери, распоредени во различни правци, тангенцијален, попречен правец. Постојат различни типови на федери преку кои што се поврзани овие елементи за различни потреби, материјали и така натаму. И она што е карактеристично е што сите нелинеарности се сконцентрирани во овие федери. Што значи дека сите деформации се случуваат во контактот помеѓу елементите, а самите елементи остануваат недеформирани. Со тоа се намалуваат степените на слобода кои што представуваат одредено ограничување во методот на конечни елементи, на пример од 24 кога станува збор за волуменски елементи на 6, што значи побрзо решавање. И огромен проблем кој што методот на конечни елементи го има, тоа е компатибилност помеѓу јазлите, која што во овој случај апсолутно не е потребна да се следи, затоа што станува збор за контакт помеѓу површини кој што се остварува преку самите федери. Исто така не е потребно однапред да ги предвидиме локациите каде што може да се случат одредени нелинарни однесувања. Представува метод кој што ја применува за решавање на равенките директна крутост, има супериорна ефикасност и прецизност и елиминира еден од проблемите кои што го има методот на конечни елементи, тоа е shear locking. Методот на применети елементи можеби ќе останеше во некоја фиока или во некој текстуален код, доколку не беше комерцијално достапен преку софтверот кој што се нарекува Extreme Loading for Structures, производ на Applied Sciences International, кој што наоѓа доста голема примена во ситуации како што се екстремни оптоварувања, инцидентни оптоварувања, динамички влијанија и така натаму. Овдека се наредени оние кои што и самиот производител ги посочува, а во оваа презентација ќе се задржам на некој од нив, а тоа е влијание од експлозија, прогресивно рушење, судар, односно проектил, односно сеизмичко влијание. Значи се ова се примери од нашето досегашно искуство. На почеток ќе представам пример кој што се однесува за анализа на зидани конструкции, односно во случајот симулација на експериментално испитување на зид на циклично оптоварување, во кој што е применет моделот на упростено микромоделирање. Во случајот се земени предвид вертикално оптоварување, сопствена тежина, вертикално оптоварување и хоризонтално циклично оптоварување во својата рамнина, без да навлегувам многу во детали. околу самите материјални модели кои што се искористени, ќе предам веднаш на финално резултатите. Споредени се хистерезисните петелки на експерименталните тестови и нумеричките симулации и за повеќе различни конфигурации на овие ѕидови, генерално може да се заклучи дека во поглед на однесување, симулација на ова однесување дава одлични или добри резултати, добра корелација во однос со самиот експеримент. Она што е исто така значајно е визуализацијата на механизмот на лом, кој што покрај представувањето преку диаграм на самото однесување, исто така ни ја доловува ситуацијата, односно состојбата на симулираниот експеримент. Во вториот случај ќе прикажам пример на прогресивно рушење. Во овој случај го одбрав чисто од една инженерска љубопитност која проработе, за жал во тој момент се работи за добро познатиот колапс на стрешницата во Нови Сад, на железничката станица, која што сите знаеме дека однесе 16 животи и која што во тој момент кога ова го работевме, се претпоставуваше дека е причината поради проблеми со корозија, излекување на овие затеги кои што ја носат самата конструкција, што на крајот преку видео снимките кои што беа достапни во јавноста видовме дека предизвика еден прогресивен колапс. Повторно ќе напоменам дека ова не беше поттикнато од некое, да кажам, истражување кое што беше во насока на детекција на точните причини, едноставно, како што реков, од љубопитство со голем број на предпоставки во моделирањето, ме интересираше дали навистина е причината она првично откачување на затегите од десната страна на самата настрешница, и за таа цел беше изработен делумен модел, како што реков, со предпоставени карактеристики на материјалите, на елементите, димензии кои што нешто беше достапно во тој момент во јавноста, и сценарио кое што беше симулирано е токму откачување на првите два десни јазли од набораната конструкција, кое што за жал го потврди детектираниот механизам на лом виден во видеоматеријалите. Значи прогресивно рушење на самата настрешница. Третиот пример е примерот кој што обработува проблем на инцидентно влијание, односно експлозија, која што во овој случај е симулирана во армирано-бетонски релативно мал објект, како форма на некаков бункер, кој што е испитуван на Политехничкиот универзитет во Мадрид, во кој што од аспект на моделирање е применет пристап на computational fluid dynamics методот и во комбинација со методот на применети елементи. Идејата е да се провери механизмот на лом, однесувањето на самата конструкција од влијание на експлозија која што се наоѓа во средината на овој затворен дел. Се работи за армирано-бетонска конструкција со дадените димензии. Во аспект на симулација на механизмот на лом, на одговорот практично и на поместувањата кои што се следени во одредени точки, методот на применети елементи во овој случај даде одлично поклопување помеѓу експерименталните, односно ситуацијата која што беше предизвикана на лице место на самиот објект, овдека може да се забележи доста добро поклопување, условно кажано, на пукнатините кои што се појавиле во самата армирано-бетонска конструкција, поглед и одвнатре, што значи дека механизмот на лом, да речеме, верно го следи она што е предизвикано во реалноста, но овие куси анимации овдека може да се забележат и главните дилатации по случување на самата експлозија која што е симулирана во самиот софтвер, како и механизмот на лом кој што има самиот солвер, значи има капацитет да ги следи овие крути тела кои што под влијание на експлозијата се разлеваат секаде во просторот, што е многу блиску до она што се случува во реалноста. И на крај последниот пример, иако во трудот има уште еден, меѓутоа од аспект на време, се одлучив да го презентирам примерот на удар на проектил во конструкција која што е потикната од своевремено тестирање спроведено во Германија, познатите мепен тестови на плочи, кои што се иницирани од нуклеарната индустрија за спречување на влијание од проектили или на нуклеарните електрани. Се работи за плоча која што во експериментални услови е испитувана под влијание на удар кој што може да биде предизвикан од така наречен тврд проектил. Постојат два типа на вакви проектили во зависност од ефектите кои што ги предизвикуваат. Овој проектил е едноставен цилиндер исполнет со лесен бетон кој што се пушта под одредена брзина да делува на самата конструкција. Во овој случај споредбата на резултатите кои што се добиени со методот на применети елементи е извршена во споредба со експерименталните резултати, меѓутоа уште еден труд кој што е работен своевремено во DAY како еден од сеопфатните софтвери кои што го користат методот на конечни елементи. Без премногу повторно деталите да ги објаснувам, може да се заклучи дека исходот од симулацијата верно ги следи резултатите и во едниот случај и во симулацијата со DAY и во експериментот, така што може или да се верификува, да се потврди уште еднаш, да се потврдат можностите на самиот пристап за анализа и во поглед на мерените големини и во поглед на механизмот на лом, односно начинот на рушење. Што да заклучиме на крај? Многу можности, докажан прецизност во поглед на услови кои што имаат некои екстремни сценарија, нели, на оптоварување, алатка која што може да ја користиме со доверба и која што значително може да ги отстрани оние ограничувања кои што ги имаме во моментот, односно да го искористиме потенцијалот за проектирање на побезбедни конструкции. И ќе завршам со последната реченица која што повторно потикната од мотото на овој симпозиум и целата тематска поставеност на темите, која што вели when structures reach their limit, AAM reveals what happens next. Благодарам.
Thank you, Professor Kurilov, for giving this insight into, let's say, structural analysis under extreme conditions. And thanks to your to keeping the time, almost keeping the time, we can allow one short question. Do you have any question? Comment, maybe? Maybe I can ask you something. What is the right size of elements if you apply your AEM? In the first example, when you had the brick structure, it's clear that you take the brick. But what do you do in a continuous structure like a reinforced concrete?
Yeah, you can play with the size. So you can, as a user, you can use different mesh size. In this case, for example, for the bricks, you can also cut the brick in half, because usually the failure in these cases can happen through the bricks also. So you can take also this into account. But it's upon the user to decide on the mesh, similar to the finite element method. But when we compare, a much denser, much coarser mesh of these solid elements is required to reach the level of accuracy in comparison to finite element model. So the solver is quite fast.
Okay, thank you very much. Thank you for presenting, and now we're coming to our last presentation.
The last presentation is with title Decarbonization of Cement by Introducing Supplementary Cement Materials, Fly Ash and Recycled Concrete Finesse. It was written by a group of authors by Ane Ančev, Goce Bogdanovski and Goce Cvetkovski, and presenter will be Ane Ančev from the USIE Titan Group.
Good afternoon to everybody. It's a pleasure to be part of these lectures. Today I will speak about the muscle, let's say, of the old constructions that we have discussed previously. We have mentioned that most important is standardization, but one of the topics, keywords of these sessions, I can say, is decarbonization of civil structures. I'm coming from Titan Usje, so we have, let's say, long history, rich history. We are producing cement since 1955. We are part of Titan Group since 1999, so 1998. So we have rich experience because Titan Group is established in 1902. We are a leader in the region in cement production and implementing of best available techniques. Our industry, cement industry, is responsible for approximately 8% of total CO2 emissions. So our main target is to tackle this topic and to give solution to part or to total reduction of these emissions. One of the key players of this is a reduction of clinker content in cements by introducing supplementary cementitious materials. Titan Usje was doing this in the last 20 years, producing Portland fly ash cement. Here is the table where it shows how this has, let's say, progresses. In the past, well-known CEM1 was the most used cement type. Here is, let's say, a kilogram of CO2 emission per ton cement. Next are, let's say, the cements of family of CEM2, CEM2AV and CEM2LL. But the biggest difference is given by introducing CEM2BV fly ash cement, CEM2BP puzzolanic cement, and also composite cement, CEM2BM, and newly established, latest, let's say, in the EN standards, CEM2CM cement. So we have to focus on this right side of this graph. Supplementary cementitious materials are well described in the EN standards. The benefits of using them are, let's say, we can clean our landfills or decrease their volume and use their technical performance. But we have to think locally because we have to use materials that are available in our environment. So we are focused as Titan Usje in utilization of fly ash, natural puzzolana, and in the future of recycled concrete fines. So our next, let's say, strategic focus is optimization of fly ash cements, also Portland composite cements, CEM2BM, CEM2CM, and development of Portland recycled fine cements. I will focus later now on the results that we have. So we can see that all this cement that I have mentioned from the family of CEM2A, CEM2B, CEM2BM, we can produce those results of the cement paste. So we can see that initial setting time is comparable. So we can see that workability and we have prolonged initial setting time of fly ash cement and composite cement, which is very beneficial for this region since summer temperatures are, let's say, like cements with long initial setting time. But the most important is the right side of this graph, where is shown the final strength development of these cements. So we can see that all of these are very comparable, but on the lower part of the graph, we can see the clinker to cement factor. So even though we have decreased drastically clinker content in the cement, we have succeeded to reach stable and repeatable high compressive strengths. Also, this is, we didn't stop by examination of cement. We are very interested in how this material will influence in the concrete. So here are results, let's say, of the slump of the concretes, especially for this type C2530. So we can see that they are very comparable. And we can improve this same 2BM, the right one, the blue one, has the lowest, let's say, slump, but with proper development of the admixtures, we can reach even better results. The tests are in progress. And also here is the table where we are showing the results of early strength of concrete and also the final strength of concrete. We can see that all of this cement can reach the same value of final strength, which is most important part, let's say, of the concrete behavior. And we are very proud that we have managed to reach this. And at the end, the Europe, also our country, we are facing that, let's say we have an issue with many old buildings that most of them has to be demolished and built new ones. And this will create demolition waste. So thanks to the new EN standard 197-6, recycled concrete fines are introduced. We are witnesses that in Switzerland there already produced cements with substitution of up to 12% of this waste. But we have to be careful because there are some issues like high water absorption, possible contamination, and low inherent reactivity. But all of this can be solved by their co-processing and with some, let's say, activities like carbonization, calcination, thermoactivation, alkali activation, so we can have them as raw materials. Our target is this construction waste to be treated as valuable new resources for our industry. So at the end, we want, let's say, Titan Nusie under the, let's say, cap of Titan headquarters to be a leader in this low carbon cement solution, but also we need huge support from the business sector, locally here, academia, of course, and especially from the governmental institutions in order to support us and to make our life easier by giving us opportunity to use these materials in a proper way. So if there are any questions, please.
Thank you, Ance, for the presentation. It is really necessary to do papers like this because carbon neutrality is very important in these days. I mean, it will be also in the next years. So it comes that we must produce cement with a low emission of CO2. We have time a little bit for a question. If anyone in the audience have questions, or may I ask something about the recycled concrete finance? What do you mean by recycled concrete finance? Is it all concrete or some specific parts of the concrete?
Actually, this is some part of the concrete demolition waste that has to be extracted from this, let's say, pile of material. And according to the standard, we need to, let's say, answer to some questions because there are some standard demands that this material has to have in order to be used as a raw material in cement production.
Yes, that I was thinking, but I wanted to emphasize also for the audience.
Yes.
Thank you for the presentation.
I'm really looking for our next cooperation of some of these projects.
Yes, of course. Thank you for all the presenters that they are keeping their time for the presentation. And so with this, we are closing the 6th session and we are inviting on lunch.